Welcome to Science Week, and this is the more geoscience or meteorological oriented talk. I welcome Professor Nielsen-Gammon from Texas A&M University. I want to briefly review his accomplishment. He sent me his CV, and that is 61 pages. That tells already a lot. So Dr. Nielsen-Gammon has over 60 publications and over 100 public media relationships, several books published. He's currently the director of the Southern Regional Climate Center, the director of the Texas Center for Climate Study. He's also Regent Professor of A&M and the State Climatologist. He's also served as a faculty member in various other study programs and departments in A&M. He worked also in the dean as associate dean in the College of Geoscience at A&M. He got the Presidential Faculty Fellows and several outstanding awards in forecasting editorial award and also outstanding teaching awards in A&M. He made his PhD from MIT in 1990 and worked for 2 years 1 year as a postdoctoral fellow at New York State University at Albany, and then became faculty at A&M in 1991. So we are looking forward for the talk to learn more about Texas weather and future climate change.
Okay, thank you, Dr. Ringeth, and thank you for the invitation to be here and speak on climate change and Texas's extreme weather. A lot of what I talk about is going to be based partly on a report that we released last year called Assessment of Historic and Future Trends in Extreme Weather in Texas. It's a complicated URL to get there, but you can just Google my name and extreme weather, and you'll probably get it right off the bat. But I'll go beyond this to talk about the science of extreme weather and extreme event attribution, and also talk about some of the more interesting extreme weather that Texas has experienced recently. And lastly, make a few remarks about how climate change affects natural disasters and how the changing risk of natural disasters actually affects people. And then we'll open it up for questions. So the way that we relate climate change to extreme weather is based on basically 3 different lines of knowledge. And I didn't come up with these. This framework is based on a National Academy of Sciences report that came out a few years ago on extreme event attribution. And basically the idea is there's 3 somewhat independent lines of evidence, and if all 3 line up in support of a climate change role, then scientists can be fairly confident about the reality of such a role. If evidence is lacking in one or more of these areas, then confidence in role of climate change is correspondingly weaker. First line of evidence is the data record. What are the historical trends in this particular type of extreme event phenomenon? Is there a detectable trend? Now, the absence of a detectable trend is not necessarily evidence against climate change, because the very nature of extreme weather is that it's something that happens fairly rarely, and consequently, it may actually take a long time statistically to reliably detect a trend within some level of confidence. And so the quality of the data and the nature of the data can be very important for whether or not you can get this aspect of evidence to line up. Second source of evidence is climate model simulations. These are global models of the climate system. Present-day models include simulations of the atmosphere, the ocean, the land surface, water cycling through the system, including ice, as well as the biosphere and how that's interacting. All of these are interconnected. And of course, like any other model, a global climate model is just a model. It's generally a simplification of what happens in reality. Hopefully it includes all of the important physics that are involved, but just from the nature of the model, it's never going to be an exact match of the real world. So the way I think of it is they're simulations of a climate system very much like our own system. And if a climate model simulates a trend in this particular type of extreme weather, that says that a climate system similar to our own, obeying the same laws of physics, produces a trend. That's evidence in favor of climate change acting to produce a similar trend in our real world. The third type of knowledge is physical understanding, our basic understanding of how the climate system works, the laws of physics, things like conservation of energy, for example. Based upon what we know about the simple laws of physics and the more complicated ones that apply to the climate system, would we be able to say that there ought to be a trend given a change in this particular aspect of the system? And if so, what's the sign of that trend? What would we expect to happen? What's the magnitude we should look for? And we can tell from that sort of thing whether, for example, the historical data would be adequate to detect such a trend if such a trend were present. So you can think of this as a three-legged stool, although if one of the legs is missing, the whole thing doesn't fall over. It just means our knowledge is incomplete, and we can't be as confident about a change actually taking place. Now, one thing we are quite confident about is global temperatures increasing. This is a chart showing the rate of change of temperature over various historical periods in the state of Texas using simulations and observations. And because as state climatologist, I do a lot of climate outreach, I'm going to be framing this in terms of degrees Fahrenheit. Here, degrees Fahrenheit per decade. And what we see is the bars get higher as you go to the right, which means that the rate of change of temperature is increasing. The climate change is accelerating within the state of Texas. And the fact that the blue bars for the simulations line up pretty well with the corresponding green bars, which are the observations, indicates that climate models are consistent with the trend that we observe. And the third line of evidence would be physical understanding. And we understand that if there's less energy escaping to space than is being absorbed from the sun, then the climate system's gaining energy and its temperature will go up. So about the most confident thing we can possibly say about climate change is that the climate system is warming. And that happens to apply to Texas, and it actually applies to just about every single square inch of land and water surface on Earth. Now, the rising temperature matters for extremes. There's basically two types of climate extremes. One is the sort of climate extreme where you've got this range of typical values, and when you got the tail of the distribution, the very rare events, those are extreme events. So for example, in Texas, summer extreme heat is often measured by the number of 100-degree days. And even if the variability of temperature doesn't change, the mere fact of the average temperature itself getting warmer means that you'll get more events at one of those tails, the high end, and fewer events at the other tail, the low end. And based on historical data, this shows basically that the average number of 100-degree days increases by about a factor of 2 for every 2-degree increase in the average temperature. This data point over here in the upper right, by the way, is the year 2011, which was a memorable year. And we understand why it was so hot. Basically, if you have so little precipitation as we did during that year, a lot of the sun's energy is going to go into just heating up and baking the ground. And a word of warning for right now, we're in the middle of a drought in much of Texas. If we don't get decent amounts of rain in the next couple of months, we may see another data point sort of filling in this gap in terms of high temperatures and 100-degree days. But now the historical trend of extreme summer temperatures doesn't show much of an increase. We actually had some pretty hot years in the 30s and the 50s, for example. And part of the explanation for that is probably associated with what's happened to Texas over that period. Back in the 1930s, we didn't have large reservoirs in the state. We didn't have many acres under irrigation like we do now. We didn't have cities where people irrigate their gardens. So quite possibly a lot of the lack of trend may be due to compensating processes. Average temperatures increasing, at the same time local conditions have changed. Now that's not so for winter extremes. Over on the right-hand plot, we have on a similar scale, the trend in the coldest temperatures in winter months over the past 130 years or so. And winter cold has been getting milder at the rate of about 1 degree per decade for the past 4 decades. Now, I don't have the year 2021 added onto this. It didn't get very cold in December 2020. It didn't get very cold in January of 2021. But February of 2021 was pretty darn impressive for cold weather. This is a map of the departure from normal temperatures during the peak of the cold event, basically around sunset on Monday, February 15th. And you may not be able to read some of these numbers, but most of the numbers in Texas and Oklahoma are below -40, meaning more than 40 degrees Fahrenheit below normal temperatures for that date. And the cold was certainly not limited to Texas, extended all the way up to Canada, but the particularly unusual aspect of this was that very cold air made it all the way down to the latitude of Texas, where admittedly we're not very used to it. The actual temperatures on February 16th, that Tuesday, were below zero across most of North Texas and the Panhandle, except for the inner parts of Dallas and Fort Worth itself. The urban heat island helping a bit, keeping temperatures less extremely cold than they might have been. But the entire state was basically got down to 30 degrees or below, freezing for the entire state. And the maximum temperature was pretty cold also, did not get above freezing except for these orange areas in South Texas and in West Texas along the Rio Grande. North Texas barely made it into the double digits Fahrenheit. And that's one reason I'm using Fahrenheit here. Double digits in Celsius is not all that impressive. Double digits in Fahrenheit is pretty darn cold. And another unusual aspect of the event was it wasn't just cold for a day, it was cold for a week. The average minimum temperature for North Texas was around 10 degrees, and the average maximum temperature was around 25 degrees. So this seems like an extreme event. We certainly, none of us here can remember very well an event like this. Let's look at it historically. This is a plot of the average minimum temperature across the state of Texas on particularly cold days in the past 130 years. The winner is 1899, where the average temperature was below zero. Now, I know nobody in the audience can remember 1899, but that's what we climatologists are for, to refresh people's memories of historical events. 2021 comes out 11th on this list, and 15th. February 15th and 16th both make the top 15 list. But the event wasn't so historical for how cold it got, it was historical for how cold it stayed. So in terms of the coldest maximum temperature, comes in third on the list, behind 1899 and 1989. And here I've looked at average temperature weighted by the distribution of population within the state. So paying special emphasis on what happened in Dallas, Houston, Austin, San Antonio, so forth. Because the big impacts of the cold were caused not by so much how cold it got throughout the state, but how much demand for electricity there was for heating, and how many people were affected by the lack of heating when the power went out for extended periods of time. And for super extended periods of time, we can do the same thing for the average temperature for the entire week, in which case the February 21 event comes in second coldest on record. A virtual tie with 1899 and exceeded only by an extended cold wave in 1983. And not just that, there's more. We also had a big snowstorm at the same time. I looked at the fraction of the state affected by some of the biggest snowstorms in Texas history, as well as the typical amount of snow spread out across the state. And 2021 is the highlight here, is basically the third most extreme or fifth most extreme snowstorm in the state of Texas, depending on how you count it. So you may have heard that climate change is making all extremes worse, including extreme cold. That's not the case, actually. It's a generalization. It's a bit of an overgeneralization. I already showed you that the coldest temperatures were actually getting warmer. So the historical record says climate change is not making extreme cold in Texas worse. Second leg of the argument would be climate models, which also say that there should be fewer cold days and the cold days should be less extreme. As to why that should be happening, there's basically two fundamental things to consider. First off, temperatures overall are getting warmer, so that should make cold extremes less cold. And since our cold weather comes from the Arctic, which is warming faster than the globe as a whole by a significant margin, our extreme colds should be getting milder. Now, the counter-argument to that is some evidence that the jet stream patterns may become a bit wavier and be more likely to bring cold air southward. But that's not as fundamental a connection, and it doesn't line up with those other two lines of evidence. So, as with many things in science, it's not written in stone, but the evidence strongly indicates that extremes such as we had in February should become less likely over time, not more likely. And the widespread snow, same basic story. Historically, there's been fewer events with snow. The models say there should be less snow in Texas. And here, at least, there's a good reason to expect snow should increase, which is warmer temperatures allow for greater amounts of moisture within storms and greater production of precipitation. So in places like Canada and Antarctica, where most of the time it's cold enough to snow, when it snows, you're going to get more snow. But it turns out in places like Texas and the Southeast and the Mid-Atlantic coast, the key question for the amount of snow you're going to get is not how much moisture is there, but is it cold enough to snow? And most of the time in Texas, it's not cold enough to snow. And as temperatures increase, it'll be even less likely to be cold enough to snow. And furthermore, when it does snow, temperatures are typically just below freezing. Well, when it does snow in the future, temperatures will typically be just below freezing also. So that temperature effect really doesn't apply to places like Texas that are on the margin of the rain-snow line. So both the intense snow and the intense cold should become less frequent in the future. So that's the good news. The bad news is if you have something which is 50 degrees below normal and temperatures go up by 4 degrees, it'll only be 46 degrees below normal and still be quite a natural disaster. Okay, another aspect of natural disasters that I've been doing a lot of work on recently is extreme rainfall. And this is a result of a statistical analysis of how the variations of extreme rainfall over time are temporally aligned with changes in the global climate in terms of global mean temperature or radiative forcing. And so this is an analysis of basically how the expected amount of rain that should occur with a 1% probability in any given year. So we call that a 100-year event. But how much rain would that be based on our analysis according to climate conditions in 1960 versus climate conditions in 2020? And there's more green dots than yellow dots, which means that individual stations show more trends positive than negative. It's a bit of a noisy plot. You certainly wouldn't want to trust an individual time series to tell you what the underlying climate-driven trend is. But perhaps you could average over the state of Texas and get something more robust. Realistically, you probably want to look over an even larger area to be more confident. So let's look over a larger area and average together a bunch of stations and look at the trends. And even now, there's some variations geographically that may not be reliable in terms of being caused by climate change. Could just be random stuff like Hurricane Harvey hit southeast Texas. It didn't hit South Texas or Alabama, and that's going to affect the trends to some extent. But lumping data together, it's even more predominantly green rather than yellow. If we look even farther off to the East Coast, you get the same basic picture. And the tale told is that the amount of extreme rainfall in an extreme event seems to have increased by around 10 to 15% on average over the past 6 decades or so. And the climate has warmed globally by about 1 degree Celsius over that period. So we can say, based on the observational record, a trend is going on of about 10 to 15% increase in intensity per degree of warming. Now, that's one line of evidence. Second line of evidence, do climate models predict an increase due to global warming? Answer is they do over most of the globe, except for places where rainfall amounts are decreasing rapidly. Third, what's our physical understanding of this? Mainly it's something I alluded to earlier. Higher temperature air can contain more water vapor. And so certainly when you get a heavy rainfall event, the atmosphere has as much water as it can hold. In fact, more than it can hold. That's why it's precipitating out. So all other things being equal, you expect increased rainfall intensity. Now, the other factor is not everything might be equal. You might have changes in the patterns of storms. You might have changes in storm structure. At least based on computer model simulations for Texas and most of the United States, those changes are small compared to the changes in temperature itself. Plus, they're probably a bit of an amplifying effect, especially for hurricanes, which seem to become more compact and intense with hurricanes. So extreme high temperatures and extreme rainfall clearly seem to be increasing due to climate change. Extreme cold, not increasing due to climate change. What about drought? That's a big issue. And now we get into something that's really complicated, frankly. People think of drought as being a lack of rainfall, and that's just that's true, that gets you in the door, basically. And it doesn't help for predicting trends in drought in Texas that the latest climate models predict 0 change in rainfall per degree of warming, plus or minus 10% or so. So there's a big range of climate projections, but they're centered on 0. So we don't know whether rain is going to increase or decrease. Historically, it has increased, so that's evidence in favor of an increase. But there's no solid physical understanding for why it should have increased so much. But rainfall controls how much water is coming into the land. Temperature, to a large extent, is controlling how much is going out. The hotter it is, the greater the evaporation rate. And temperatures, obviously, are increasing. So even if rain stayed the same, the climate system would become drier because the water wouldn't stay in the soil as long, so it would dry out more rapidly. Another important factor is the timing of the rainfall. In the state of Texas, typically we go from October through April adding water to the soil. So the soil has the most water around mid to late spring. And then in the summertime, temperatures skyrocket, rainfall doesn't keep up, and so things dry out. According to the climate models, if rainfall does decrease, it's most likely to decrease in the summertime, which would imply increased drought, even if rainfall increases in the winter, because we won't get as much rain when we really need it. Other aspects, the intensity of rain will affect the amount that soaks in versus running off. Plus, carbon dioxide means plants might not need as much water, but if they don't need as much water and therefore grow more vigorously, that might cancel things out. But then natural variability, things like La Nina, are so important for Texas that even knowing the climate trend wouldn't allow us to reliably predict drought circumstances in any given year. Okay, I want to wrap up by talking about how climate change manifests itself in societal impacts. Now, the actual risk for climate change disasters changes gradually and usually imperceptibly, because you don't know it's happening until the event happens, or unless some scientist comes along and says, hey, we did this statistical analysis, trust us, it's accurate. Most people aren't going to buy into that unless things actually happen that they can see them happening. So you get these climate-related disasters, such as, say, Hurricane Harvey, that happen very suddenly. We see the impact suddenly, and societal awareness of the risk goes up. Also, our changes in our perception of that risk goes up because those events happen. So, talk about billion-dollar disasters. This event from Hurricane Harvey, this is an image of what was happening in Hurricane Harvey, and extremely damaging, obviously. But I argue that this is a similar billion-dollar disaster. I argue that I should have made this window a little bit bigger so you could see it, but oh well. This is a semi-random street in the Dallas area. It turns out it's located right next to the 100-year floodplain, which means, according to historical analysis, the chances of flooding here is greater than 1 in 100 in any given year. And along that street, that beautiful street, it's less than 1 in 100. But that's according to the historical analysis based on historical events. As you've seen, the trend is upward, and as time goes on, we'll see more and more of those heavy events. Now, maybe this area will get hit by a flood, and like Harvey, you'll suddenly have massive economic loss. Or maybe we'll just have the statistical analysis of the assessment of that risk increasing such that eventually this area is rezoned as being within the floodplain. And when that happens, simultaneously, it's more expensive to live there because your insurance costs go up. And if you can't afford to live there anymore, it's more expensive to sell because who wants to buy a house in the floodplain where they have to buy flood insurance? So you have massive economic impacts from the changing risk of extreme weather, even though the extreme weather itself may not actually happen in a particular location. So to summarize, I've focused a bit on the February cold, which ranks fairly high up on various metrics, but probably wasn't a climate change event insofar as all of those aspects of extreme weather should be becoming less likely because of climate change. Lesson there is you can't really generalize for all extremes with a blanket statement. It's pretty complicated, depends on the particular extreme event and the particular circumstances. And unfortunately, it's also challenging to do something about it because anything that says the risk is increased is a true economic cost for many people who may not be able to afford it. But unfortunately, we're stuck with some measure of climate change no matter what we decide to do about it.